Welcome and thank you for joining me in this lesson. Recall that in this unit we've learned about vectors and how to operate with vectors. Remember that when we operate with numbers, we have to follow certain rules, which are all summarized by what we call the BADMAS rule. The same thing applies to operating with vectors. So when we operate with vectors, we need to follow certain rules, and all the rules are based on properties of vectors, and that's what we are going to talk about today. So remember that we have the commutative law for vector addition, which states that vector A plus vector B will produce the same resultant and it's vectors B plus A. So the order in addition won't matter. The associative law, two vectors A plus B added to a vector C will produce the same resultant as vector A added to vectors B plus C. Properties on scalar multiplication. So if M and N are two scalars, then M times N times vector A would equal M times the vector NA. If a scalar M multiplies the sum of two vectors, it will produce the same resultant as scalar M times A plus scalar M times B. And M plus N, the two scalars, multiplied by vector A, give MA plus NA. We've also mentioned the properties of the zero vector, which states that vector A plus vector 0 would give vector A, and each vector has a negative or an opposite, such that, for example, if the vector is called A, when you add the opposite of it, then it will give vector 0. We also talked about projections, and we said that the projection of A on B, which is written as projection of A onto B, equals the dot product of vectors A and B divided by B dot B, and then multiplied by vector B. Next, we talked about how to multiply two vectors, and we said that there are two ways of multiplying two vectors, by using what we call the dot product, also known as the scalar product, and that's because we get a number when we multiply vectors by using dot product, and the cross product. So the properties in dot product are, if two vectors are perpendicular to each other, then u dot v equals 0, and that is because dot product is based on the formula magnitude of u, magnitude of v, and then cosine of angle theta. If angle theta is 90 degrees, that will make cosine equal to 0, which proves that the two vectors, or which tells us that the two vectors will have the dot product of 0. The next is what we call the magnitudes property. It applies to multiplying a vector with itself in a dot product. In this case, the angle theta will be equal to 0, therefore the cosine theta would be equal to 1, because cosine of 0 is 1, which leaves u dot u equal to magnitude of u squared. The associative property with a scalar states that if we have a scalar k multiplying vector u dot v, the product u dot v, then that would equal ku dot v or u dot kv, which means that the scalar can go with either vector. The distributive property states that if we are dot producting a vector u with the sum of two vectors, that would be equal to u dot v, so you apply this just like you expand a polynomial, plus u dot w. Commutative property states that u dot v and v dot u will produce the same result. We also went over the dot product in unit vectors. So we said I dot j is 0, and that is because I and j are perpendicular vectors. Similarly, I dot k is 0 because they are perpendicular, and k dot j is also 0. So a unit vector dot producting itself would be 1. That's because the angle is 0, which makes cosine equal to 1. So The same thing applies to I dot I and K dot K. Next, we went over properties of cross product. So if we have three vectors, A, B, and C in 3D, then we're going to say that A cross B would be equal to the opposite of B cross A, which means that the order in multiplication matters. It will produce the same vector, but it will be going in the opposite direction if you switch the vectors around. Remember that the cross product is also known as the vector product because the result that we get from cross product in two vectors is another vector. Now, next is the distributive law, which states that a vector A crossing the sum of two vectors B and C would give A cross B A plus A cross C. And the scalar law states that K, A cross B would be KA cross B. So K can go with the first vector or it can go with the second vector. A similar property was seen in scalar product as well. Important to remember is the cross product between the unit vectors, because the magnitude of the cross product of a vector is found by multiplying the magnitudes of each vector times the sine of angle theta, the sine made between the two of them. Then remember that sine theta would be 0 for angle 0 and angle 180. And sine theta will be 1 for 90-degree angles. So what that means is that if we cross product two perpendicular vectors, then we're going to get a vector equal in magnitude to the product of the magnitudes of each vector. And when you cross product a vector with itself, which means the angle is 0, then the cross product will be 0, which is illustrated here. Now, we said that when angles the vectors are perpendicular, sine theta will be 1. And we're going to say that I dot j will equal k j dot k equals I k dot I equals j. Now, when we change the order, j cross I, k cross j, I cross k, then we're going to say that the vector will be opposite because we follow what we call the right-hand rule. So these were all the properties. Now let's take a look at a couple of examples. In the first example, we have to prove the distributive property in dot product. So for this, we are looking at vectors A, B, and C with the coordinates as indicated. And we have to prove that A dot B plus C equals A dot B plus A dot C. So we're going to start with the left side, which is A dot B plus C. And we'll substitute the coordinates and simplify. We'll do the same thing with the right side, which is A dot B plus A dot C. We'll simplify until we see that the two sides will simplify to the same expression. So let's get started. What we have in here is A, which is XA, YA, ZA. Now this is dotting B plus C. B is XB, YB, ZB, plus vector C, which is XC plus YC plus ZC. Now remember that these are in brackets, B and C. Let's start simplifying inside the brackets first. I'm going to bring this a little to the left so we have a fair amount of space on both sides. So for now, we're going to start off with brackets. So we have XA YA, ZA, which is dot producting. So remember here, to add two vectors, we add the respective coordinates. So XB plus XC, comma, YB plus YC, ZB plus ZC. So now we'll dot product them. Remember, in dot product, we multiply the coordinates and we add them. So what we have here is XA multiplying XB plus XC plus YA multiplies YB plus YC plus ZA multiplied by ZB plus ZC. So as you can see in here, again, notice how we multiply the x's together, we multiply the y's together, and then we multiply the z together, the z's together. Let's choose a different color here, right here. So next we'll expand. So what we get here is XA, XB plus XA, XC plus YA, YB plus YA, YC plus ZA, ZB plus ZA, ZC. So far this is the expression and we won't simplify any further. Now let's take a look at A dot B plus A dot C. So again, what we have in here is vector A. Let me just separate them. So we have XA, YA, ZA, dot producting XB, YB, ZB, and then plus, so we're talking about this plus right here, A, which is XA, YA, ZA, dot producting X, Y, Z of C. So in dot product, again, remember that we're multiplying the x's together, the y's together, the z's together, and add them all up, which means that we have x of A times x of B plus YA, YB plus ZA, ZB. So practically what we're doing here is, so the x's together, the y's together, and the z's together. And then plus XAXC plus YA, YC plus ZA, ZC. So same idea here. So we multiply the x's together, the y's together, and then the z's together. So now let's take a look at what we have obtained in each case. So we have XAXB. Here we have XAXC, which is right here. YA, YB, YA, YC, ZA, ZB, and ZA, ZC. So in total, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 terms. As you can see, left side equals right side, which proves that A dot B plus C equals A dot B plus A dot C. Next, we're going to take a look at example number 2, where we're given vectors A, B, and C, 3 vectors in 3D, and we have to find A dot B cross C and B dot B cross C. So remember that when we multiply these vectors, we need to first multiply B cross C. We need to multiply B cross C to obtain a vector so that we can dot product A with B cross C. Remember that if you multiplied A dot B, you would get a scalar, and you do not want to cross a scalar with a vector. So let's go. B cross C. We're going to list the vectors B and C, which are 1, 2, and 0. And vector C, negative 1, 5, 3. And here is I, J, K. I, J, K. Draw the line. And we'll go down products first, and then up products next. So for down products, we have 3 times 2, 6i. 0 times negative 1, 0j. 1 times 5, k. So 5k. Now subtract the up products. 5 times 0, I. So this 0 actually belongs here. 3 times 1, j. Negative 1 times 2, k. So negative 2k. So we have 6i minus 0i plus 0j minus 3j plus 5k plus 2k. So this would be 6i minus 3j plus 7k. This would be vector B cross C. And now we have to dot product it with A. So we'll say A dot B cross C equals, vector A is 2, 1, 1. B cross C is 6, negative 3, 7. So in this case, we're multiplying the x's together, the y's together, the z's together, and adding them all up. So 2 times 6 is 12. 1 times negative 3 is negative 3. 1 times 7 is 7. So here we go. We get 12, negative 3, and 7. So that would equal 9 plus 7, 16. Next, we will find B dot B cross C. You can try this on your own. Because it's very similar to what we just did. So you start off with B cross C. Now in the next video, we'll go over example number 3. Stay tuned.